recording. Before starting today's lecture, so there is a typo in my note, in particular in ODE part. So actually, suppose you have say x0, which is hyperbolic equilibrium point, no? And then I wrote down there that a hyperbolic equilibrium point is asymptotically stable if and only if all the eigenvalues of df of x0, that matrix, are negative. Actually, it is not if and only if condition, it's kind of typo. So I have means whenever I just typed it, no, it's a typo. So it is just the if condition. So that means that hyperbolic equilibrium point is asymptotically stable if all the eigenvalues of df0 are means the positive part are negative. Okay, so it's a typo. I made it as a if and only, but it is only the if condition. Okay. Okay, so that is the typo. So one student actually pointed out. I have not means whenever I make a note, I try to review it completely, but it's by it's a typo. So yeah, please check these things there. Okay, so what we are discussing. Yeah, so today we'll continue on Laplace equations. So we have seen the properties of harmonic functions, okay, in particular maximum principle and so on. And then actually what we have seen that if it is a harmonic functions, they are basically infinity functions, and not only that, how the derivative can be bounded by the integral of that functions and so on. And as an important theorem, which is called the Liouville theorem, what it says that if I give you any bounded harmonic functions on Rn, then it must be constant. Okay. So now today, as I said, that our main goal is to prove the existence and uniqueness of this equation, kind of the Poisson equations, minus Laplace of u is equal to f in omega, where omega is a bounded domain, open bounded domain with a smooth boundary, and u, which is g on del omega. Okay, so first we try to know whether this problem has a unique solutions or not. Okay, so I put as a theorem. Existence part is it's a different issue that I'll talk about little. I'll just mention it, but at least what you can say that if this problem has a solution, then it is unique. What it says that, so for that I need g, it should be continuous on del omega, and f is continuous on omega. And then there exists at least one. Okay, so there exists at least one solution u, which is C2 on omega intersection C2 omega closure, means it can be extended on omega closure continuously. This is C2 in omega, means 2 times differentiable, and the derivative, the second derivative is continuous. That is the meaning of C2. Intersection C of omega closure of the IVP star. Okay, this is my star. What it says that it does not guarantee that whether problem has a solutions or not. What it says that if this problem has a solution, that means the U is in C2 omega intersection C of omega closure such that it satisfies star, then it is unique. We cannot have two solutions, U1 and U2, such that it satisfies this equation. Okay, then U1 must be U2. That is the uniqueness theorem. Let's prove it. So for that, we try to use so-called the maximal principle, whatever we have done it for harmonic functions. So proof. Now suppose there exists two solutions. Okay, suppose I have U and V, which is C2 omega intersection C of omega closure, such that they solves C star. Okay, now I define W, which is a U minus V. Then your W is in again C2 omega intersection C of omega closure, is it not? And not only that, I have that W is equal to 0 in omega and W is equal to 0 on del omega, because U is equal to G, V is equal to also G on del omega. So U is equal to 0 in omega, W is equal to 0 on del omega. Is it not? So by maximum principle or the weak maximum principle, what I know that the omega attains its maximum on the boundary. Is it not? That means my W, which is less than equal to maximum of W over omega closure, which is actually same as maximum of our W over del omega, which is 0. So I have W is less equal to 0. Now I can use also the minimum principle, no? Because already we have seen that whenever we are having this the harmonic function, so then the maximum principle and then the minimum principle also hold. So that means what I can see there, that the minimum of W over omega closure, it's attains the boundary, that is the minimum of W over del omega. So from there what I have, so by minimum principle, what I have, W is greater or equal to 0. So this implies W is equal to 0, hence U is equal to V. Okay. So what it says there, if this Poisson problem has a solution, then it is unique. We don't know whether it has a solution or not. That is a different question. One need to ask it, but one can prove that this problem has a solution. So that is a different issue. We will not going into that. But what it says here, that if this problem has a solution, then it must be unique. Okay. So we'll consider another approach, that is called the variational approach, to find out whether this problem has a solutions or not. So for that, I need to define so-called the energy functional. I define my space X, which is all those U is in C2 omega intersection C of omega closure, such that my U is equal to G on del of omega. Okay. And I'm defining my functional J, which is my this space X to real number R. How I am defining that J of U, which is half of integral over omega gradient of U square minus integral over omega f of U. Okay. So I'm defining my space X, which is in this form, that is called the energy space, and I am defining the energy, which is J function from X to R, such that J of U is equal to half of integral over omega mod of grad u square minus integral omega f of d. Okay, so what I'm trying to say that if u is a solution to your Poisson problem, that star, if and only if it is a minimum for this functional j. Okay, so theorem u belongs to C2 omega intersection C of omega closure is a solution of Poisson problem star if and only if that j of u, which is minimum where v is in my space X of j of v. Okay, this is sometimes called the variational approach or the Dirichlet principle. Okay, so how to prove it? What theorem states that if u is a solution, then u must be the minimum of this functional j. On the other hand, if we have a minimum for this functional, say u star, then u star must be solution to my Poisson problem. Okay, let's prove it. So now suppose my u is a minimum for this cost functional. That means, okay, so suppose j of u is equal to minimum of v is in my x, j of v. So that means u is equal to g on del omega and u is in C2 omega intersection C of omega closure. So then what I have to show that? I have to show that u satisfy my given equation, that means minus Laplace u is equal to f in omega. Is it not? Because boundary condition, since u is in my x, already I have defined my functional space. Okay, the solution space such way that u is equal to g on del omega. Okay, so now this is a functional, so and j has a minimum at u, so I can think of a real valued functions. Suppose I have a b from R to R, maybe I define it, where my b of t is equal to say j of u plus t phi for any phi which is a cis infinity function. Okay, this is smooth function with compact support. Okay, so if I do these things, then what I have, that my b, it has a minimum at t is equal to 0, because j has a minimum at u, so b has a minimum at t is equal to 0. Since it has a minimum at t is equal to 0, I can think of that the derivative at t is equal to 0 is equal to 0. So what I have, b has a minimum at t is equal to 0. Okay, so it is something like that whenever you are doing this Taylor's expansion, for multidimensional case, then actually, you are just considering one-dimensional setup, and then we know the Taylor's theorem from there, and then try to get back for your multidimensional case. So here what it says that since my j has a, because j is defined on some energy space x, okay, which is kind of infinite dimensional things and so on. But here I try to find out on a finite dimensional setup. That means it is a function from R to R, real valued functions, and then I am having this part. So this implies that d dt of j of u plus t phi at t is equal to 0, that gives you 0. Okay, so let us try to find out what is my j of u plus t phi. So j of u plus t phi you check it, this should be, so j is this one, so you replace u by u plus tp, then what I have, half of integral over omega get u square plus t times integral over omega get u dot get phi plus t square by 2 integral over omega get phi square minus integral over omega f of u minus t times integral over omega f of phi. Okay, is it not? Okay, so always dx and so on. So now what is this? If you differentiate it, so this implies 0, which is my ddt of j of u plus tp at t is equal to 0. So now if you differentiate with respect to t, I have this part, and then here I have t, but at t is equal to 0. So no, and now I have this one. So the effective term is basically this term and then this term. So I have, this is nothing but integral over omega get u dot get phi minus integral over omega f of phi. Is it not? So what I need that minus Laplace u. So now if you use again the divergence theorem from here, okay, so what I have, this is integral over minus sine integral omega Laplace u of phi, okay, and then there is no boundary term because phi has a compact support. So I can think of some ball, okay, which has a smooth boundary, ball of say radius some r, such that the support of phi contained in there, and then this integral is same as integral over that ball, and then this part, and then you have a ball. So now we have a normal for the ball. Normal, you know how to find out, okay, and then that gives you 0. So there is no boundary term, okay, because phi has a compact support. So I have this part minus integral over omega f of phi, which is nothing but integral over omega Laplace u plus f of phi. So at the end, what I have, integral over omega Laplace u plus f of phi is equal to 0, and this holds for all phi belongs to cc infinitive of your omega. Okay, so now since this holds for all phi in cc infinitive over omega, so and this Laplace u plus f, they are basically continuous. So what I know that this function should be 0 within omega. Okay, so this implies this part already you have seen it, no? That integral over fv is equal to 0 over sum ab, then and it is continuous functions and so on. So from there f is identical to 0. We have seen it in your analysis course. So that is kind of generalization for that. I have, if this holds for all phi cc infinity of omega, then it can be said that Laplace u plus f is equal to 0 in omega. This implies minus Laplace of u is equal to f in omega. So already, since u is a minimum, already I know that u is equal to z on del omega, and u is in c2 omega intersection c of omega closure. And now I have this part. That means the minimum of j, which is now u, is a solution to your Dirichlet problem, okay, or the Poisson problem. Okay, so now we'll prove the converse part, that suppose my u is a solution to my given problem, then what can you say about whether this u minimizes your functional energy function or not? Conversely, so let u solve the problem. Okay, so this implies u is in c2 omega intersection c of omega closure, u is equal to g on del omega, and minus Laplace u is equal to f in omega. So that means u belongs to my space x, is it not? Okay, So what I have to show? I have to show that for any arbitrary v is in my x, j of u is less than or equal to j of v. Then we are done. Is it not? Then it says that u is a minimum of your j. U lies in also x and j is less than or equal to j of v because v is in arbitrary element from x. Okay. Okay. So this part actually we try to show it. Okay. So now look at what I know, that minus Laplace u is equal to f in omega. So from there what I can have, minus Laplace of u, if I consider, say, if I multiply it by v minus u, this should be your f of v minus u. Now you integrate with respect to omega, okay, over omega. So then what I have, this part I had. So now again use the divergence theorem. From there what I have, I can throw one derivative here. So this is integral over omega grad u dot grad of, because this is now the vector v minus u. Okay, and then the boundary term, but there is no boundary term because what I have, I can write down this is v minus u and then dou u dou nu. Is it not? But v is equal to, v is from x, so v is equal to g in del omega and u is equal to g on del omega. So v minus u is equal to 0 on del omega. So that means on del omega there is no boundary term involved here. Okay, so I have only this term. This is equal to integral over omega. This is a b because it is linear, integral over omega f of u. So now these things is what? This is nothing but integral over omega grad u dot grad b, because this is again linear, minus integral over omega gradient of u square, which is equal to integral over omega f of b minus integral over omega f of u. Okay, so this implies if I took this minus sign to the right hand side, and if I take this side, what I have, integral over omega grad u square minus integral over omega f of u. This is equal to integral over omega grad u dot grad v and then minus integral over omega f of b. Is it not? This part I am taking in this side. So now this part I can write down. So what I know, that AB is less than or equal to half of a square plus half of b square. If I use this formula, then what I have, this term is less than or equal to half of integral over omega grad u square plus half of integral over omega grad of b square minus integral over omega f of b. Is it not? So now I have here 1 half. So this implies in the left hand side I have half of integral over omega grad of u square minus integral over omega f of u. This is less than or equal to half of integral over omega grad v square minus integral over omega f of v. Is it not? So now what is this one? This one is nothing but my j of u. No, the energy function also I have defined. This is j of u, and this part is nothing but j of v. Okay, and this holds for all v is in my the solution space X. Okay, and now since this holds for all v, that means v is my arbitrary and u is in also my X, or I can conclude that j of u, which is minimum over v is in X, j of v. Okay, this I want. So this theorem says that the u, which is a C2 omega intersection C of omega closure, it would be a solution to your Poisson problem if and only it is a minimizer to this energy functional J. Okay. Okay. Okay, so now so far what we have considered it, we have a bounded domain, and then first we have proved the uniqueness If solution exists, then it will be unique using your maximum principle for harmonic functions and so on. And then actually we have seen that the variational characterizations of the solutions to this problem. So now we want to move on. What happened in Rn? So I want to know whether there exists a solution for minus Laplace u is equal to f in Rn or not. Okay, so for that we first try to find out so-called the fundamental solutions. Why it is called fundamental solutions? Actually, we try to first know that is there any solution which satisfies minus Laplace u is equal to 0 or not. Okay, and then if you have a minus Laplace u is equal to any f on the right hand side, I can write down the solutions to this minus Laplace u is equal to f in Rn. Okay, with some good function f, means I need some assumptions on it, no? Because for any problem we may not have a solution, so we need some assumptions. Okay, so whether I can write down the fundamental solutions or not. So that is why that solution I am going to discuss it. It is called the fundamental solutions of Laplace equation. Okay. So what I try to find out that we try to find out the solutions u of Laplace equations in Rn. Okay, in whole Rn. So for n is equal to 1, it is R, n equal to 2, it is in R2 plane and so on. Okay, so but we try to find out the solutions of this form u of x is equal to v of some r, where mod x is equal to r, means kind of the radial solution. Okay, so we try to find out the radial solution, so that minus Laplace u is equal to 0 or Laplace u is equal to 0, and from there I try to deduce that v, it may satisfy some differential equations, and so that we can solve it, the differential equations. So now idea is, if ux is equal to v of r for mod x is equal to r, then what is your okay, so from here I know that dou r dou xi, this is nothing but your xi by r, no? Because mod x is equal to r, so dou r dou xi, this should be basically xi by r. Okay, and then what is your u of xi? Okay, which is the partial derivative, no? I partial derivative u of xi. So this should be, you have br, so this is v prime of r, and then dou r dou xi, which is nothing but my xi by r. Then what is your u xi? Again I try to differentiate with respect to xi. Then what it should be? It should be v double prime r, and then I have xi square by r square, and plus now I have v prime r. Okay, v prime of r, and then the derivative of xi by r. So then what I have, if we use this, is 1 by r, and then minus xi square by r cube. Okay, so this implies I need Laplace of u. Laplace of u is nothing but summation over I is equal to 1 to n. Okay, u of xi. So now if you see these things, it should be now summation over I xi square is equal to r square. So what I have, u double prime over r. Okay, and then plus from here you have, so v prime r. Okay, now you have your summation, that's why you have your n by r minus this is r square by r, so 1 by r, that means this is n minus 1 by r times v prime of r. Is it not? Because you are just summing over xi, and summation over xi square is equal to r square, that we know. And from here this is n, because summation over I is equal to 1 to n, you have n, so n by r minus r square by r cube, So we have n minus 1 by r cube. So what we have, because I want to find out my u is a solution to your Laplace problem, that is Laplace of u is equal to 0. This is happening if and only if these things is 0. P double prime r plus n minus 1 by r, g prime of r is equal to 0. Okay. So now these things actually you can write down. This is r to the power n minus times b prime of prime. Okay. So this is r to the power n minus 1 b prime of prime, that is actually is equal to 0. I can write down. This is 0. So I can write down this implies this is 0. And hence what I can have b prime, because you have the whole prime, so what I can write down, this is some constant a by r to the power n minus 1 for some constant a, is it not? If you just integrate from here, I have this part. So now if my r is positive, what I have, so if r is positive, then what I have b of r. So r is positive means basically x is not equal to 0. B of r. So if you again integrate these things, what I have, this is b times log r plus c for n is equal to 2, and this is some constant b by r to the power n minus 2 plus c for n is greater or equal to 3. Okay, so we try to deduce the fundamental solution for Laplace equations in Rn. So then idea is, okay, suppose I have a radial solution, means u of x is equal to v of r for mod x is equal to r. And then if u satisfy your equation, then what kind of equation should satisfy, means b should satisfy what kind of equation. So then what it says that b should satisfy these things. So that means b of r, for r is positive, it should be b of log r plus c, and for n equal to 2, and for n greater or equal to 3, this is b by r to the power n minus 2 plus c. So, and where this b and c, they are the constants. Okay. So now taking the motivations from this, we define the following. That is called the fundamental solution. The function I define p of x, this is minus 1 by 2 pi. So these constants I am having, but I need to find out a particular constant way, that is log of mod x for n is equal to 2, or 1 by n into n minus 2 times alpha of n. We have already defined alpha of n is nothing but the measure of ball of 0, 1. Is it not? 1 by mod x to the power n minus 2 for n greater or equal to 3, which is defined for x is not equal to 0. Okay, and x is in my r of n in general. This is called fundamental solution of the Laplace equation. Why it is called fundamental solution? So you'll see little later that, as I say, that if I try to solve that minus Laplace is equal to f, okay, then actually we can find out that if I define my u is equal to p convolution f, okay, with some f, I need some assumptions on f, then you solves this Poisson problem in Rn. Okay. So that is why it is a fundamental solution, because from that solutions actually you can generate for nonlinear problem and so on. Okay. So that I'll come back. But what it says that the function phi of x is defined in this form, and that is how we are defining it. Actually, it is just coming from the motivation that we are looking for the radial solution for the Laplace equations, and from there it is equivalent to find out reduces to your its ODE, okay, whose solution is given by in this form, which depending on the dimension for n is equal to 2 and for n greater equal to 3. The interesting property of phi is the following, that phi and gradient of phi, they are locally integrable. Locally integrable means basically if you consider any compact set, okay, and then if you consider the integral of that compact set, that is always finite, that is called the locally integrable. Okay, for any compact set if you consider, then phi and grad phi, they are finite. Okay, so that is locally integrable. But dou square phi dou xi dou xj is not locally integrable. In particular, if you just consider on a ball of 0, 1, then these things is not integrable. Okay, so if that implies that it is not locally integrable, because for locally integrable for any complex set it should be integrable, but we will see that on there actually it is not integrable. Okay, so this is the second derivative, dou square phi dou xi dou xj, it's not locally integrable. But the good thing is that x goes to phi of x, which is the fundamental solution, is harmonic for x not equal to 0. Okay, and that is why that if I consider x of phi of say x minus y, okay, so as a function of x, so is harmonic as a function of x. That means Laplace of x phi of x minus y, that is equal to 0 for x not equal to y. Okay, so for x not equal to y, this is a main important property for that. Okay, so these are the properties of your fundamental solutions of Laplace equations phi. I am not going into do these proofs, that will take more time, but what I try to say that phi and then gradient of phi, it is locally integrable, but the second derivative means dou square phi dou xi dou xj is not locally integrable. In particular, as I said, that you just consider the set ball of 0, 1. From there, actually, you'll see that it is not locally integrable. There is a blow up. But good point is that x goes to px for x not equal to 0 is harmonic, isn't it? Because you try to, as I told you, say that we try to show that Laplace phi is equal to 0. So Laplace of u is equal to 0, and then from there we are looking as a radial functions, and from the radial functions we deduce the function v, how it looks like, and from looking at that we try to define these functions. Okay, so it is a harmonic for x not equal to 0, and hence the x goes to phi of x minus y is harmonic as a function of x for x not equal to y. Okay, so as I told you that why it is called the fundamental solution. So for that, I have the following theorem. Let f is in CC2 of Rn. Okay, that means it is twice continuously differentiable with compact support. Okay, then if I define my u, which is phi convolution f, which is belongs to C2 of Rn. So what is your convolutions? You know, integral over Rn. So that means u of x, which is this is phi over x minus y and then fy dy. Is it not? This is the convolution, and we know that the convolutions is associative, means it's commutes, which is same as phi of x and then f of x minus y dy. You also find, is it not? Means f convolution phi is same as F, phi convolution F is same as my F convolution phi. Is it not? And this is okay on the, if it is locally integrable, no? If it is locally integrable and so on, then I can define the convolution. So in this case, phi has a compact support. Okay, so we are in a good position. Okay, so claim is that this U, which is phi convolution shape, which is defined in this way, it solves so this is now my C2 of Rn. Okay, so I cannot put that C intersection of omega closure, no, because that is of bounded domain. We have proved it here actually. No boundary between on whole Rn, no. So C2 of Rn, that is actually I need, and it solves minus Laplace U is equal to F. So it solves minus Laplace U is equal to F. Okay. So what it says that, so on the other hand, actually, I'm not going to do the proof. So you can just look at the proof, means in my node, actually, I have given the proof. So you just have a look, or in the other words, if time permits, I'll do the proof, but I don't think that I have enough time to discuss these things. But I'm trying to say that actually I don't need F is in CC2 actually. Only thing is that if F is in CC1 also, this theorem holds. Okay, so I can say, so whatever the proof, actually I have done it in my node, that is for F is in CC2. But one can, remove that kind of restrictions. It should hold for F belongs to CC1 of Rn, and still my U, which is phi convolutions F, it is in again C2 of Rn, and it solves your Poisson equation minus Laplace is equal to F in whole Rn. Okay. It is just the convolution things actually you try to find out, and that the property, if you consider the derivative for this convolution, so that if you consider the one derivative for that function, that is, this is also fine. Means what I'm saying, that dou u dou xi, this actually I can think of that this is dou f dou xi convolutions phi, or F convolutions dou p dou xi. Is it not? This actually this is exist. Okay. You will see that these are the property for the convolutions, and not only that, if you think of my dou square u dou xi dou xj, this is actually I can write down phi convolution dou square f dou xi dou xj. Okay, and now dou square f dou xi dou xj, this is continuous and phi is locally integrable. Hence, your these things is continuous. Okay, this is also continuous, and hence from here what you can see that my U, which is in C2 of Rn, is it not? Just the properties of the convolutions, from there you check that it is C2 of Rn. Okay, and now we try to put it that, okay, that minus Laplace Ux is equal to F, minus Laplace U is equal to F. So for that you start with Laplace of Ux. So for there actually you can think of some integral on ball of say 0 epsilon, another is outside of that, and then you try to manipulate that part, so it will then come. Okay, so please look at my notes, and if you have some problem, then I will discuss it. But it is there. So because of the time constant, I can't continue the proof. But the message is that I know that fundamental solution for the Laplace equations phi, which is given by this form, This is depending on the dimensions of your domain, means in Rn. So n is equal to 2 or n greater equal to 3. I have these expressions, and the important property is that phi and gradient of phi is locally integrable, but this is not the locally integrable, the second derivative, and it satisfies your harmonic, means it is harmonic for x not equal to 0, and hence x goes to phi of x minus y is harmonic as a function of x for x not equal to y. Using that, actually, if I give you a function f which is either cc1 Rn or cc2 Rn, then the phi convolution f, it is in c2 Rn. Not only that, it satisfy my Poisson problem minus Laplace is equal to f. Okay, so as I said that this theorem holds for f is in cc of Rn. Okay, so this is for the fundamental solutions which is defined on whole Rn. No, I want to solve the problem minus Laplace is equal to f in Rn. So this is solvable because phi convolutions f is a solution to that problem. Okay, so now question is, if I try to solve it minus Laplace u is equal to f in omega, suppose my omega is a nice domain, means omega is a bounded domain with C1 boundary. Okay, with C1 boundary. And u is equal to g on del omega. So we have seen that if this problem has a solution, then it is unique. Okay, but question is, can I find out the solutions to this problem or not, or the general representation formula for the solutions of these Poisson equations? Okay, so then the idea is, okay, that is called, so to find out that call, we need to find out so-called the Green's function. So I'll define that Green's functions, but that depending on the domain, the Green's function depending on the domain. For arbitrary domain which is which has a C1 boundary and open bounded domain, we cannot find always the Green's function, but for a specific domain we can find the Green's function, and hence I can find out the solutions to this problem or the representations representation for the solution to this problem. Okay, so what I want to find out, so now say phi, okay, maybe look to Green's function. So now phi is your fundamental solution. Okay, so I try to fix my x is in my omega, and let u, which is C2 omega intersection C of omega closure. Okay, or basically I put at C1 omega closure. Okay, C1 omega closure. Now we consider this function y goes to phi of y minus x. X is now fixed. Now I am looking for y goes to phi of y minus x. Okay, so then what I have, that integral over omega difference ball of x epsilon, for any epsilon is positive. Now Laplace of uy and then phi of y minus x of dy. X is fixed, so I am differentiating with respect to y. So these things I can write down by using your Green's formula. This is integral over del omega union dou b of x epsilon, and then what I have, that dou u dou nu of y phi of y minus x minus u of y dou phi dou nu of y minus x, and then d sigma y, because other term is 0, no, because Laplace of phi y minus x for y not equal to x, that is 0, because that is harmonic, no, that is actually we have seen that x goes to phi of x minus y for x not equal to y is harmonic. That means Laplace of that part is harmonic. So now we can use this Green's formula to deduce this part. Okay, so now if you just pass to the limit as epsilon goes to 0, this part as epsilon goes to 0, okay, so this part is integral over omega Laplace u of y t of y minus x of dy. Okay, so now this right hand side, I have this right hand side. So this right hand side I can write down, put as this is RHS. RHS I can write down, this is integral over dou omega. The same thing else I can write down, dou u dou nu of y p of y minus x minus u of y dou p dou nu of y minus x and then d of sigma y, and then plus, because it is the union of that boundary, I have dou b of x and epsilon, dou u dou nu of y p of y minus x minus u of y dou p dou nu of y minus x and then d of sigma y. Okay, so now this thing, I have my this part. So now as epsilon goes to 0, okay, what I can check that this part is converges to integral over dou omega dou u. This is fine because there is no epsilon kind of thing. So you take it a. So this is my a, but this part, okay, as epsilon goes to 0, whatever I am having, so this goes to 0. It is just basically u of x. As epsilon goes to 0, okay, so it will goes to u of x. So that means if I just add this left hand side and then right hand side, what I have, u of x is equal to minus integral over omega Laplace u of y t of y minus x dy plus integral over del omega dou u dou nu of y p of y minus x minus u of y dou p dou nu of y minus x and then d of sigma y. Okay, so now u solves your problem. Okay, u solves the Poisson equation. That is actually we are just assuming that suppose my u solves the Poisson equation. That means what I have, that I have minus Laplace u is equal to 8. Okay, so from there what I have actually, I have u of x is equal to integral over omega. This is Laplace of u, so I can have f of y p of y minus x of dy. No, if you solve Poisson equation, because minus Laplace u, that is actually 8. So I wrote down f of y p of xy plus integral over del omega dou u dou nu of y p of y minus x minus g of y, because u is equal to g on the boundary. This is g of y dou p dou nu of y minus x of d sigma y. Okay, so now the normal derivative, which is dou u dou nu along del omega, this is unknown, is it not? So what I try to find out here, that suppose you solve my Poisson problem, okay, and then I have this expression, but in this expression the problem is that this dou u dou nu, we don't know how to calculate. It is unknown, is it not? Along the dou of omega, the boundary of your domain, this is unknown. We don't know how to find out. So this motivates us to find a correction function that we denote, say, P of x, y, which solving the boundary value problem. That Laplace of Px y is equal to 0 in omega, and P of x y is equal to P of y minus x on del omega. So this function Pxy, it is called the Green's function. Okay, so later on actually we'll see that Pyx minus Pxy is called the Green's function. Okay, I'll stop now. So I'll continue from here. This is just the motivations how to define the Green's function for any domain, but we may not be able to find out for any domain. So I will find out for the particular domain now. But these are the motivations that how to find out the Green's function, because we want to solve the problem, or we want to have a solution representation for this Gaussian problem minus Laplace u is equal to f in a bounded domain with C1 boundary. Okay, so I'll stop now.